In today's lecture, we'll be taking a look at organometallic chemistry, oxidative addition reactions. So what is an oxidative addition reaction? Well, it's a process where the oxidation state and coordination number of a metal center increases. So here's a general example of an oxidative addition reaction, and you can see we're starting with a 16 electron complex and we end up with an 18 electron complex. So the overall electron count of the complex increases by 2, even though the oxidation state of the metal has increased. And in general, it increases by 2. And we've actually already seen an example of an oxidative addition in this course. The formation of a Grignard reagent is formally an oxidative addition, where you're starting with elemental magnesium, and then you form an alkyl or aryl magnesium halide starting from an alkyl halide or an aryl halide. So in this case, the oxidation state of the magnesium goes from 0 to +2, but the overall electron count of your magnesium has increased by 2 electrons because you formed two metal ligand bonds, two X-type ligands. So the way an oxidative addition works is that you get a net transfer of 2 electrons from the metal into the sigma star orbital of this AB bond here. And then you get a transfer of the electrons in the AB sigma bond into a metal ligand bond. So what ends up happening is this cleaves the AB bond and forms two new metal ligand bonds, one to A and one to B. So here would be a sigma star antibonding orbital for AB, and you can imagine that an oxidative addition is almost like a pi-acidic interaction where you get back bonding from the metal, but you actually end up getting so much back bonding from the metal that both of these electrons fully occupy the sigma star antibonding orbital. And that fully breaks this AB bond so that these electrons then jump in between the metal and B and form an MB bond. So the reverse of an oxidative addition is a reductive elimination reaction, as shown here. And theoretically, every oxidative addition is in equilibrium with its corresponding back reaction or reductive elimination. However, even though it's potentially reversible, in practice, you generally only go in one direction. It's very uncommon to get a balanced equilibrium where oxidative addition and reductive elimination are in competition with each other. And what actually drives the direction of these reactions is thermodynamics. So that's the relative stability of the different metal oxidation states in your starting complex and your product. It also depends on the strength of the AB bond versus the MA and MB bonds that are formed during oxidative addition. And shown here is an example where you have a palladium 0 complex that is 2-coordinate right here, and it's oxidatively adding this bromobenzene here. And then you form a 4-coordinate palladium 2 complex that's square planar. And the reason this reaction is driven pretty much to completion is because the benzene bromine bond is fairly weak in comparison to the palladium carbon and palladium bromide bonds that form. And it's actually the palladium carbon bond that especially drives this reaction because of its very high strength. So if oxidative additions and reductive eliminations are theoretically in equilibrium with each other, but they're generally driven to one side due to thermodynamics, the question is, how can you favor an oxidative addition? How can you drive this reaction to the right and prevent the back reaction? Well, another way of phrasing this question is, how do you stabilize the products? Or how do you make the starting materials more reactive? Well, to make the metal complex more reactive, you can have a lower oxidation state. And this makes the metal more electron rich and more reducing. Moreover, it also makes the higher oxidation state more stable because there's less positive charge buildup on your metal center. And actually, in practice, it's relatively hard to get oxidative addition to proceed with a metal that's above the +2 or +3 oxidation state, because if they're in higher oxidation states, they just aren't electron rich enough to do the reaction. And oftentimes, in those higher oxidation states, you don't even have enough electrons to be able to perform an oxidative addition. Another way to make your starting metal complex more electron rich is to have strong sigma donor ligands and very electron rich ligands that will in turn make your metal center more reducing and more electron rich. In addition, when you form that higher oxidation state product, it is stabilized by these more electron donating ligands. So an example would be anionic ligands such as hydrides and carbanions, or phosphines, carbines, etc. All of these are very strong sigma donors. They form very strong metal ligand bonds, and they donate a lot of electron density to the metal center. Other than the metal center, you can also drive this reaction by using very strong oxidants that form more stable products upon oxidative addition. And here's just a small list of potential oxidants that are diatomic in their elemental forms. And you can see chlorine gas, which is very oxidizing, is on the higher end, whereas hydrogen, which is not as oxidizing, is at the lower end. What's interesting here is that oxygen, which has a very high standard reduction potential of 1.23 volts, is not as strong an oxidant as hydrogen, which has a standard reduction potential of 0. And the reason for that is upon oxidative addition, the hydrogen forms two metal hydride bonds, which are very strong, whereas oxygen, when it undergoes oxidative addition, forms a very high energy peroxo species, which is not very stable, shown here. And because the product of oxidative addition of oxygen is much less stable than the products of the oxidative addition of hydrogen, it's much less oxidizing specifically for the oxidative addition of transition metals. Another thing we will see is that oxidative addition often involves a ligand substitution reaction because you need open coordination sites on the metal, initially for AB to bind to the metal, and then also you need vacant sites for the MA and MB bonds that form. And along the same lines, oxidative addition is favored by sterically accommodating ligands. And the reason for that is that it allows AB to more readily bind to the metal center. And it also makes the product, which has a higher coordination number, less sterically crowded. It's also important to note that third row transition metals in general form stronger metal ligand bonds, and because of that, they are much more prone to oxidative additions than reductive eliminations. Now at this point, we're going to take a quick look at some common oxidative addition substrates. So we already saw that some strong oxidants can act as substrates for oxidative addition. So elemental halides such as chlorine gas, bromine, iodine, these all act as oxidative addition substrates. We also saw that hydrogen acts as a very good oxidative addition substrate, and even though it's not traditionally thought of as a strong oxidant based on its reduction potential, because it forms those strong metal hydride bonds, it's more oxidizing specifically for transition metals. Moreover, the pi acidity of hydrogen gas when it's a ligand also increases the oxidizing ability of hydrogen gas towards transition metals, because if you remember, oxidative addition can be viewed as an extreme form of pi back donation from the metal, so much so that the electrons are donated from the metal to that pi star antibonding orbital, causing the formation of two new metal ligand bonds. So other than hydrogen gas, things like ethylene, tetrafluoroethylene, which is much more electron deficient and oxidizing, acetylenes, etc., they can all undergo oxidative additions because they are pi acidic ligands. Strong electrophiles can also act as oxidative addition substrates, so things like methyl iodide, hydrogen chloride, etc. Organic compounds with especially weak bonds are prone to oxidative addition. So these are alkynyl halides, so sp hybridized carbons bonded to a halide. Vinyl, allyl, and aryl halides also have relatively weak bonds to halides, so that would be an sp2 hybridized carbon bonded to a halide. Alkyl halides also have somewhat weak carbon halide bonds. So these are sp3 hybridized carbons bonded to halides, and these are actually ordered according to their reactivity, with the alkynyl halides being the most reactive towards oxidative addition and the alkyl halides being the least reactive. It's important to note that things like aromatic bromides, which are kind of in the middle there, they very commonly oxidatively add to metals, but very, very rarely reductively eliminate. So that should give you something of a benchmark as to how reactive these species are towards oxidative addition versus reductive elimination. So something like an alkyl hydride, on the other hand, would commonly undergo reductive elimination, but it would be very hard to oxidatively add an alkane because carbon-hydrogen bonds are quite strong. So depending on what your substrate is, there are actually several different mechanisms for oxidative addition. There's a concerted addition, an SN2-like addition, an ionic addition, where there are two subtypes, and there's also bimolecular and radical additions. We'll be focusing mainly on the first three groups of oxidative addition, and we'll briefly touch on bimolecular and radical additions at the end of the lecture. So the mechanism of concerted addition requires the coordination of that AB oxidative addition substrate initially, and then you form a three-centered transition state where you form the new metal ligand bonds and break that AB bond. So initially, a concerted addition often will require a ligand substitution reaction followed by the cleavage of that AB bond. So shown here is your ligand substitution reaction, where one of these neutral L-type ligands is substituted by this AB substrate. It should be noted that the ligand that is substituted does not have to be neutral, it could be anionic. And what happens is that substrate binds as a side-on sigma complex, where the electrons in the AB bond are being donated to the metal center to form that interaction. And then you get strong back donation of d electrons into the AB sigma star antibonding orbital, which, if this is a weaker bond, is lower in energy and more accessible to those d electrons. This then cleaves the AB bond. These electrons are formally donated to A, and you form an Ma bond. And then these electrons go between the metal and the B ligand and form an Mb bond. It's also important to note that in this mechanism specifically, the initial product is always cis because of the mechanism where it binds side-on and then you cleave the AB bond. And because of that, your two new ligands, A and B, have to be cis to each other. However, afterwards, they can isomerize to a trans form through various mechanisms that we've learned about in this course. Lastly, you should be aware that this ligand substitution at the beginning of this oxidative addition can occur any of the ways that we've looked at, depending on the coordination number and d electron count of that starting metal complex, how sterically encumbered it is, etc., etc. The mechanism of an SN2 oxidative addition, on the other hand, is a little bit different from that of a concerted addition. So for an SN2 type mechanism, you get nucleophilic attack of the metal on the AB substrate. Another way of saying that is that an electron pair from the metal center donates into a sigma star antibonding orbital for AB. Now the first part of an SN2 type mechanism of oxidative addition is shown here. And for our purposes here, the AB bond is polarized towards the B atom, so the A atom is more electropositive. And you can see that the electron pair from the metal center is attacking the more electropositive atom of AB. And then the electrons in the AB bond jump to B, forming an anionic species. So this ends up generating your Ma bond with B as your leaving group. It's also important to note that in this initial step of your SN2 oxidative addition, your metal center is oxidized by 2 electrons, and that's why the charge on the iridium complex goes up, and B is needed as a counterion to ensure that charge is conserved for this reaction. So this SN2 mechanism for oxidative addition is very, very similar to an organic reaction where you have a nucleophile and an electrophile. It's just in this case, your nucleophile is a very electron-rich metal center, which then gets oxidized. So just like in the organic reaction, there is inversion of the stereochemistry at A, because this is an SN2 mechanism where you have bond forming and bond breaking in your transition state. Then, after the initial nucleophilic attack, coordination of the leaving group B- completes the reaction. And it's important to note that B- can coordinate either cis or trans to A, and that's because of the specific mechanism. When you get your nucleophilic attack of the metal center on A, B, your leaving group, doesn't actually form a bond with the metal center. Only the metal and A form a bond right here. B is attracted to this intermediate complex here through an electrostatic attraction, but B is free to coordinate to the metal center at any vacant site. And you can see in this particular complex, it actually coordinates trans to A. This is in contrast to a concerted mechanism where A and B have to be cis initially. It's only through isomerization that they would end up trans. Also, it should be noted that if this intermediate complex ends up being coordinatively saturated, B- can coordinate through a ligand substitution reaction. Moreover, coordination of B- doesn't always occur, and it could just end up being a counterion. But in that case, the reaction would not be a true oxidative addition. Instead, it would be classified as just an electrophilic attack of the metal on AB. So just to sum up, in this mechanism, in the first step, the metal center attacks AB and is oxidized by 2 electrons. Then, upon coordination of your leaving group B, the electron count of the resulting metal complex increases by 2 over the starting material. This type of mechanism is most common for polarized substrates such as alkyl halides, and the first step, which is the oxidation step, is actually rate limiting. So if the first step is rate limiting, what could enhance this reaction? Well, pretty much anything that would enhance the organic SN2 reaction. So a more nucleophilic metal would make the metal center more reactive and would speed up that initial nucleophilic attack step. This could be achieved by having more electron donating ligands on the metal center or having a lower oxidation state on the metal center. In addition, a sterically more accessible electrophile A would enhance this reaction because the electrophile would be more reactive and more prone to nucleophilic attack. Lastly, a better leaving group would make the electrophile more reactive, it would make these intermediate products more stable, and would favor that initial nucleophilic attack of the metal on AB. Now, for an ionic oxidative addition reaction, there are actually 2 separate mechanisms. The first of which we'll go into, which is more common and involves a nucleophilic metal center. So it's very similar to an SN2 type oxidative addition, except that you add dissociated ions rather than electrophilic molecules. So shown here, you can see this is very similar to an SN2 where you have an electron pair on a nucleophilic metal center attacking an electrophile. Except in this case, the electrophile is a dissociated ion. Then you can get coordination of the counter ion and formation of your final product. So this is common for substrates such as hydrogen halides, HCl, HBr, organic acids such as acetate, etc. And the reason for that is because they readily dissociate in solution. You may notice that for this particular example, you're starting with an 18 electron complex and you end up with a 16 electron complex. The reason for that is that there are actually two separate ligand substitution reactions that accommodate the platinum hydride bond that forms and then the platinum X bond that forms here. And these substitutions occur because the resulting 16 electron platinum complex preferentially adopts a square planar geometry due to Jahn-Teller distortions. And just like an SN2 type mechanism, this first nucleophilic attack step oxidizes the metal center by 2 electrons and generates this intermediate that has a positive charge. And then once you coordinate your X ligand, so this counter ion, you neutralize that charge. In order to enhance this reaction, very similar to an SN2 type oxidative addition, you need to make your metal center or nucleophile more electron rich. And in order to do that, you can have more electron donating ligands, or you could have a lower oxidation state metal. In this example, the triphenylphosphine ligands are actually quite electron donating, and the platinum center is in the zero oxidation state. So both the ligands and the oxidation state of the metal are making it more nucleophilic so that it can attack that proton. And with respect to those two ligand substitution reactions, you can see that this one is a little bit unusual in that the metal center is being oxidized by this proton, while you're getting substitution of this phosphine ligand. So your electron count is actually decreasing, but you can think of this like it would be an associative ligand substitution, where your incoming ligand, which becomes a hydride, forms a bond with platinum, and then you lose your phosphine ligand from a 5-coordinate intermediate. And you should be able to guess at what type of mechanism this ligand substitution with your anionic X-type ligand would proceed through. It would likely be an associative ligand substitution reaction because it's square planar platinum, it's 16 electron, it can accommodate the binding of an additional ligand, and also that hydride ligand is very small. You should also be able to justify why the triphenylphosphine ligand is the one that is substituted. And the reason for that is that the hydride has a very strong trans effect, stronger than that of triphenylphosphine. Now, for the less common mechanism for ionic oxidative addition, it actually involves an electrophilic metal center in contrast to a nucleophilic metal center. So pretty much it's the opposite of the previous ionic mechanism we just went through. So the first step involves the coordination of an anion, and this makes the metal center more nucleophilic. So in this example, you can see you have a positively charged iridium complex that is 16 electron. So it's relatively electron poor. And it first coordinates this chloride anion. This generates a neutral iridium complex that's 18 electrons, so it's much more electron rich. And then an electron pair on the iridium attacks a proton, oxidizes the metal center, increases the charge of the product, and generates an 18 electron complex because you're forming a new metal ligand bond, but you're also oxidizing the metal center at the same time. You should also be aware that for both of these mechanisms of ionic oxidative addition, the A and B ligands can coordinate either cis or trans, much like an SN2 mechanism of oxidative addition. And lastly, we're going to take a look at a couple of other mechanisms for oxidative addition that are much less common. So The first one we're going to take a look at briefly is a binuclear oxidative addition, and that's where two metal centers are involved in the oxidative addition reaction. So two metal centers have a change in oxidation state, electron count, and coordination number. Here's just a general scheme for a binuclear oxidative addition, and it's more common for metals that do not have a stable N+2 oxidation state, but instead have a stable N+1 oxidation state. It's also common for 17 electron complexes or binuclear 18 electron complexes with a metal-metal bond, as shown here. And you can see that each metal center is oxidized by one electron and forms a new metal ligand bond. So two electrons are needed to break the AB bond, and one electron is donated by one metal center, and then the other is donated by the other. And for this 18 electron complex with a metal-metal bond, you can think of these as masked 17 electron species, because when you break this metal-metal bond, one electron goes to one metal center and one goes to the other. So they actually are sharing these two electrons, but formally, if you split this apart, they each be 17 electron species. So overall, for a binuclear oxidative addition, you do get a 2 electron reduction of AB, and you do form two metal ligand bonds with A and B. The difference is the electrons come from two metal centers, and A becomes coordinated to one metal center and B becomes coordinated to the other. And the final mechanism that we're going to take a look at today is a radical oxidative addition. So this involves radical initiation, propagation, and chain termination, just like any type of radical reaction. But this mechanism is actually quite controversial because it's very difficult to reproduce any kinetic investigations done on these types of systems. And that's because the rate can change with very small impurities in your substrate, your transition metal complex, or even your solvent. So batch to batch, the reaction rates can vary quite wildly. So shown below is an oxidative addition reaction that's thought to go through a radical mechanism. And you can see that initiation starts with the reaction of a radical with an iridium 1 complex generating an iridium 2 complex that has some radical character. Now your initiator can actually be something like oxygen, or it could be an initiator that you add to this system. Then your iridium 2 complex reacts with your substrate Rx, and the key step in this reaction is the donation of one electron from the iridium 2 complex into the antibonding orbital of your substrate. And this actually forms your iridium X bond. It also generates iridium 3 and a carbon-based radical, and then this carbon-based radical can then go back and start reacting with more of your iridium 1 complex. So in this way, the carbon radical is the chain carrier. In addition, two of these carbon radicals can quench each other and form a carbon-carbon bond. So that would be your chain termination step, and that reaction actually limits the number of cycles that can go into oxidizing your iridium complex. And it also generates quite a few side products. Now there are two key indicators for an oxidative addition reaction that point towards it going through a radical mechanism. One is that the initiation of the radical chain often leads to a distinctive and observable induction period. So what do I mean by that? Well, when you do your kinetics, you're going to end up with a graph that looks like this, where it's not linear at the beginning, but it curves upwards. And this initial part where the reaction is proceeding very slowly, that's your induction period. And the second point is that you get loss of stereochemistry at your alpha carbon because you form a planar carbon radical. So this R group here, if it was chiral, would end up giving you a planar carbon radical right here, which would form two enantiomers upon binding to the iridium 1 complex. That concludes today's lecture, and if anything was unclear, please try rereading the textbook or asking questions during office hours. And as always, there are some useful websites and resources below to help with some of the material that was covered in today's lecture.